Hey, welcome to our lecture online. Now let's take a look at Reynolds number. Now the reason why Reynolds number sometimes is confusing is because Reynolds number is slightly different under different geometric conditions depending upon what the situation is. Is fluid flowing through a channel, through a pipe, between plates? Depending upon what's happening, and sometimes objects moving through a fluid, the Reynolds number will represent a slightly different thing, and the resulting numbers we get will be different for different situations. But nevertheless, it is a good way of determining whether or not the flow will be laminar or will be turbulent. So when the Reynolds number is large, you end up with turbulent flow. When the Reynolds number is small, you end up with laminar or smooth flow. So coming back here, how would we define the Reynolds number? Well, it's basically the ratio of the inertial forces divided by the viscous forces. What that means is the inertial forces are the forces of the motion of the liquid. So as the liquid or the fluid is moving through the container, moving through the pipe, moving between the plates, whatever it may be, they're interacting with the sides of the pipe or the sides of the box or the sides of the channel that they're moving through. And so the motion, kind of like the momentum of the fluid and the interaction between the sides and the interaction between the molecules of the fluid, those are called the inertial forces. And then what's trying to slow that flow down would be the viscous forces. The viscous forces are caused by the intermolecular forces and the shape of the molecules, and that's trying to slow that flow down. So if the ratio of the inertial forces trying to push the liquid through divided by the forces trying to hold it back because of the viscosity of the fluid, if that ratio is large, you'll get turbulent flow. If that ratio is small, you get smooth flow. Notice one of the factors in there is velocity, which is indicated here. Larger velocities tends to increase that ratio, therefore increase that Reynolds number, more likely to have turbulent flow. When V is small, that ratio is smaller, you're more likely to have laminar flow. Also notice that the length of the pipe is important, the density of the liquid, and of course in the denominator we have the coefficient of viscosity. Now what I wanted to do here in this video is get a better feel for the units of that Reynolds number and the units of the constant or the coefficient of viscosity. Well, first of all, since the numerator is the product of the density of the fluid, the velocity, and the length of the pipe or the length of the travel, or sometimes it can be expressed as the diameter of the pipe. So you see that depending upon what the structure is, L may represent different things here. Notice that the units for density is kilograms per cubic meter, velocity meters per second, the length is meters. If we now multiply those three together, the units then become, we have kilograms per cubic meter, and then for velocity we'll have meters per second, and for length we have meters. Notice then we have meters squared in the numerator, meters cubed on the denominator, so those two cancel out two of those, and so the units then end up being, that would be kilograms per meter times seconds. Okay, now what are the units for the coefficient of viscosity? Well, it turns out the units are pascals times seconds. And of course, a pascal is a Newton per square meter, so this can be written as, and notice I use arrows because I don't like to use equal signs. Obviously, this is not equal to that. This is just indicating those are the units of this product, and these are the units of the coefficient of viscosity. So here we have pascals, which is newtons per square meter times seconds. And of course, a Newton is the force that applied to 1 kilogram will give it an acceleration of 1 meter per second square. So the units there would be kilogram meters per second square. We have meters square in the denominator, and we have seconds in the numerator. Now, if we simplify that, notice we have meters cancels that one out, seconds cancels that one out, and so we can then say that this then simplifies to kilograms, and I'll reverse the order there, meter times seconds, which is exact same units as I have over there, kilograms, meters, divided by meters, and divided by seconds. So notice that the units for the numerator and the denominator are exactly the same, which means that the units of the Reynolds number is 0. There are no units, it's unitless. So Reynolds number is simply just a number, and it's not 0. Now, depending upon the geometry, If the Reynolds number is typically greater than 2,000 or somewhere in that neighborhood, you end up with turbulent flow. If it's less than 2,000, you generally end up with laminar flow. But that again depends a lot upon the different situations, and I'll go talk about those later in more detail in the different kind of geometric situations. But right now it's just simply good enough to realize that that's what that means. Now, what happens if we multiply the numerator and the denominator by, let's say, V times L? Let's try that. So we have Reynolds number is equal to the density times V times L divided by mu. And if I'm going to multiply the numerator by V times L, the denominator V times L, how would the units change? Well, at that point, we end up with, we have kilograms divided by meter times seconds, and then we multiply that times velocity would be meters per second, and L would be meters, and in the denominator, same thing, we end up with kilograms divided by meters times seconds, multiplied times meters per second, times meters. Notice how the units would now change. So now we end up with kilograms. This meter cancels out one of those. This meter cancels out one of those. We end up with kilogram meters per second square in the denominator, and, numerator I should say, and kilogram meter per second square in the denominator. And if you think about it, those are the units of force. And so we can say that's equal to newtons divided by newtons. And just an interesting thing to note that if we take the Reynolds number, which was equal to this ratio, and multiply both the numerator and denominator times velocity times the length or the dimension of the situation that we're in, we end up with newtons divided by newtons. Again, we're still unitless, of course, but it's just interesting because here they talk about inertial forces divided by viscous forces, realizing, of course, that the units of the numerator and denominator are not in terms of force. To get force, we have to multiply both the top and the bottom, numerator and denominator, by V times L. But at this time, I hope you have some feel for the units of the Reynolds number, realizing that Reynolds number is unitless. Also realize that the units for viscosity is pascals times second. That's always a good thing to know. And of course, that the units of the numerator and denominator are therefore equal. Sometimes they utilize dimensions to come up with things such as the Reynolds number to apply to things such as fluid dynamics. So it's just kind of a play with units, and that's really where the Reynolds number came from. That's how they did it.